Okay. Yeah, so good afternoon, everyone. And
Good afternoon, sir.
this is second lecture on cryptography. And it will be last on cryptography. Yeah, so in this lecture, we are going to learn mainly private key crypto system versus public key crypto system. So in last lecture, essentially whatever we learned, they are all private key crypto systems. And today we are going to learn public key, mainly RSA algorithm, mainly. And that RSA algorithm is based on the idea of product and factorization. So products are easier to take, whereas factorization is difficult to take. And we'll see that idea, product versus factorization. Then some basics required for RSA algorithm, namely the Fermat-Euler's theorem on congruence. And for Euler's theorem, we need Euler's phi function. So we'll do those basics. And lastly, learn the RSA algorithm. If possible, if time permits, we'll do the RSA problem and as an application like key exchange. Yeah, so that's the plan for this lecture. So let's recall what we have done in first lecture.
In first lecture, we did different types of ciphers with introduction to cryptography.
Yeah, so mainly what we learned was some person A, which we called as Alice, wants to send message to person B. And this kind of cryptography between two people where the code is mutually understood between them or mutually pre-decided, like what code they'll use for the communication, that is pre-decided, and that's called as private key crypto system. Yeah, and then A has some message, say we call it as plain text, and A wants to send it to B, but possibly there may be some third person, say Eve or enemy, who wants to intercept that message, and therefore A sends a message to B in some disguised form, coded form, and what B receives is uh, generally called as ciphertext, and the ciphertext is done using some method, some key. That key is called as encryption key. And once B receives C, B has to get back original message. So what B does is, in fact, apply inverse function of E, that is called as a decryption key, D of Y. So I'll call it E inverse. And as an example, we saw three different types of methods. One was pigpen or tic-tac-toe.
What is
-1 into 1?
yes, sir.
So that is inverse of that function E. So like for example, our E of X was, in case of Caesar cipher, E of X was like X plus 3. So you shift forward by 3. So to get back original message, what you'll do is shift backward by 3, and that is called as inverse function. So I'll call it as D of Y, decryption key, equal to Y minus 3, or that's also called as E inverse function. Like for example, square and square root are inverse functions of each other, and similarly E and D, their job will be like inverses of each other.
Okay.
Yeah. So we learned one pigpen or tic-tac-toe method where instead of letters we use symbols. Then another method cytil. So that was used by Spartans almost 2500 years before. And it's basically based on transposition of letters. So the positions of the letters are shifted by 2 places, 3 places, but A stands for A, B stands for B, and so on. So it's basically a transposition method. So I hope you remember that cylinder and you wrap a cloth around that and write in horizontal way and then unwrap it and you get the message in column or vertical direction. So that was cycle. And one third example was Caesar cipher. So used by Julius Caesar. So that is called as ship cipher. So where we shift every letter by 3. So like A, we replace everywhere by B, C, D. So shift every letter by three positions. Then B, we shift to E, B, C, D, E, right? And so on. But that is on circular disk of A to Z because like when I A, B, C, D, and so on. So I go A to D. Then as far as XYZ is concerned, X will go from Y, Z, and A. So X goes back to A, Y goes back to B, and Z goes back to C, right? So because it was circular in nature, in fact, what we did was replace every letter by number. So A was replaced by 0, B was replaced by 1, and so on up to Z. So we replace A to Z by 0 to 25. And why 0 to 25 now you know. In fact, we wanted to work uh, modulo 26, right? And working modulo 26 is like looking at reminders when you divide by 26. And when I divide by 26, the reminders are 0, 1, 2, 3 up to 25. So instead of 1 to 26, we number them as 0 to 25, right?
Yes, sir.
And the maths enters into the picture, or particularly number theory has a role in this system. So here onwards, in fact, every number theory comes into picture. Yeah, so our E of X with this was like X plus 3, but modulo 26. So for example, A is 0. So E of 0 is like 0 plus 3 and 0 plus 3 is 3. So once I get a number between 0 to 25, I keep it as it is. But if it goes beyond that, then I work it modulo 26. So so this is 3, I keep it 3 only, and that is nothing but D. So A goes to D, right? Then as far as X is concerned, so X is like 23, Y is 24, Z is 25. So, so suppose I want what should be X, so E of X, that is E of 23, and what I'll do is 23 plus 3, but that is 26, and I look at 26 modulo 26. So when I divide 26 by 26, what is the remainder? That is 0, and therefore X is A. What is Y? So E of Y is E of 24. So that is 24 plus 3. That is 27. And what is 27 modulo 26? So that is 1 mod 26.
One more.
Right? And 1 is
B.
like B. So Y goes to B and so. Okay. So somebody raise the hand.
Yes, sir.
Yes, Anahita.
Yes, sir. So I just got the logic for coding it.
but I did not quite get the logic of decoding it. I'm getting still a bit confused about it. So can you explain it
Okay.
with some examples?
Okay. So idea is like, suppose I have some word. Say for example, let's say simple word ABC, and it will get decoded as DEF. So this is coding, right? Now, as far as, suppose if I receive DEF from Alice, what I should do? I should go back 3 places backwards, or like D. So I'll get CBA E, and I'll get DCB F. I'll get EDC. Right, so I'll get 3 places back. It's shifting by 3 places forward, and therefore to get back original message, I have to shift backwards by 3 places. That is the idea.
Yes, sir, I got
So
that.
in terms of this congruence, I said D of Y. So suppose I receive, so this is original message X, this is Y. So what I'll do is Y minus 3 modulo 26. Right?
Okay. Yes, yes, yes. Got it, sir. Got it.
Or in particular, if you have doubt with some kind of calculation, you can ask me whatever.
No, sir, if you could just give a few words for decoding, or sorry, yeah, decoding, that would be really nice. I would just have a practice with that. Like the like I could do the coding more easily than the decoding. That's the main question.
Basically, that's the idea of cryptography. Like uh, decoding should be a little more confusing than coding, so that the third party won't understand what we are doing.
Okay, yes, yes.
But
Got it.
anyway, it's just part of practice. And nowadays, with the help of computer, all these things are easy. Yeah. So then this was Caesar cipher, and then more generally, there is nothing special about that shifting by 3. So more generally, what one can do is E of X is equal
So
to,
shift cipher, sir. We even did that one.
yeah. So we did shift cipher. So E of X is X plus K, but because there are 26 letters, we are doing modulo 26. But if you add some more symbols like comma, full stop, and so on, then this list of 26 may get extended to 27, 28, 29, 30, whatever. So where K is in number between 1 to 25. I don't take K as 0, because if K is 0, E of X would be X, the original message. So there won't be any encryption as such, or no tricky part in that. So it will be just the original message sent to B.
Sir, it can be more than 25 as well, right? Because then we are going in a mod 26 clock.
So K can be 1 to anything between 1 to 25. So you can shift by 1 place, 2 places, 3 places, like Caesar shifted by 3 places, 4 up to 25. Now shifting 25 places is like going back 1 place, right? Because everything is on a disk, on a clock, right?
Sir, shouldn't it be K greater than 0, less than 25?
Yes, so you mean K strictly greater than 0?
Yeah, yeah. Greater than or
Yeah,
equal to
that is
0.
correct. No, if I mean, mathematically speaking, you can take K as 0, but if I take practically K equal to 0, what I'll send is basically E of X equal to X. So I'll be sending the original message as it is to B, and then there won't be any confusing part for the third party.
Okay, okay, okay. Got it. Got it.
Yeah. Yeah. So in this case, D of Y is like Y minus K mod 26. So these are all private key crypto systems. Then in fact, a little more general was affine. So where what we do is, just to make it little complicated, we do some 8 times X. So maybe 2 times, 3 times, 4 times, and so on. So sum multiple times of x plus b mod 26. But I have condition on A in this case. To get back original message, I need my A such that GCD of A and 26 should be 1, because in that case I can find out inverse of A. So if I take AX plus B as Y modulo 26, so AX is equal to Y minus B, and to get back X I have to multiply by some suitable number so that here A and that number cancels and I get 1, right? But in modular arithmetic, I don't have some fractions like 1 by 2, 1 by 3, and so on. So for example, suppose I have say 7x, or maybe let me take some small number, say 3x. If I multiply by 9, it's 9 3s are 27, and 27 modulo 26 is like 1. So I'll get back original x, right? So I have to multiply by some number which I'll call as A inverse. So I'll call it as inverse of A, and I'll get back original x, that is A inverse y minus b. And though I'm writing it as A inverse, it's not going to be some fraction or 1 by something. It's number out of 1 to 25 only. But it's such that the GCD of A and 26 is 1. Then only I can get such A inverse. Right? That's the idea.
So can you repeat why a power minus 1 is not 1 by a?
What,
Sir,
what
you
is
said
not 1 by?
so you said a power minus 1 is not 1 by a, right?
So this is just symbol or notation I'm using for inverse. So like for example, suppose I have say 3x equal to something, say y minus 1. I want x, and I have reminders 0 to 25, and I'm working modulo 26. So I don't have something like 1 by 3 or something, but I want, so what is the idea of 1 by 3? So when I multiply with 3, 3 and 3 cancels and we get 1. So like in case of real numbers, I have 1 by 3, which when multiplied with 3 is 1. So in case of this modular arithmetic, modulo 26, I have to multiply by some suitable number, which will give me 1. So for example, say for example, here if I multiply by 9, 9 3s are 27, and 27 is same as 1 modulo 26. So I get 1x, so that is x. This is modulo 26. Okay, and that 9 I am calling as inverse of 3, 3 inverse. So I don't have in real sense fractions, but I have inverse which give me.
Sir, we are dividing.
Right?
Sir, we are dividing y minus b by a. So what if that is not integer? Means can it happen?
Sorry, it's not in practical sense division. In some sense, we are multiplying by inverse modulo 26. So just a minute. So this was 9, right? So anyhow, I want to get back original x, that is the idea, and to get back x, I have to get rid of that a, and therefore I have to multiply by some number which will give me 1 there. And these all things can be done modulo 26 if GCD of A and 26 is 1. Yeah, so that was affine crypto system, fine, which was more general than shift, or we multiply x also by some suitable number a to get it more and more complex for the third person to hack it or crack it. Fine, any doubt? Yeah. Shall we go
So
ahead?
can you transform one letter to another letter by this affine cipher? Can you
One.
one example? So you gave an example that x equals 9y minus 9, right?
Yeah.
Can you do it with that letters? Like, can you transform one letter to the another letter?
Maybe at the end in our RSA also, I need to find inverse. So there we'll do again one example. Okay.
Okay. Okay.
So yeah. And anyways, all these things are not actually, they're not difficult. So they're easy. It's part of practice because congruence arithmetic is something new to you. So don't worry about this. These are easy and standard things. So if you take some number theory book like David Burton and so on and practice some problems, these will be easier for you. So it's not confusing. Yeah. Okay. Now for all these things, so essentially the basic point is when A and B decide upon some method, so beforehand A and B should meet each other and they should uh, discuss like for this week or for this month we'll be using this and this technique or this method and so on. So that's called as key exchange, right? So A and B have to meet each other for exchanging the keys before they start working with some method. Otherwise, even B won't understand like what A is sending. Okay. And like in situation like Corona, or if suppose A and B are staying far off, then this may not be practically possible. So some mathematicians put the idea like, can we exchange the keys without meeting? Right? And key we exchange without meeting. So that is on some secure channel.
Sir, we can mail it or something.
Yeah, but like even mails, someone can hack or right. So
Keeping
can
person
it
to
be safe?
person.
Can it be exchanged in a safe manner? That was the point. And one idea is this. So so I'm telling you idea in principle, like what could be done. See all these communications like mail, WhatsApp or whatever, telephone, everything can be hacked by the hacker, right? So by the third person. So how we can make it more and more safe? That's the problem. That's the point. So one idea is this, and this is in principle. So I'm telling you uh, essentially what should be done in terms of cryptography, but I'm telling you some practical example. Like suppose say A sends a message to B, and whatever key they are going to use for next month or next week or whatever. So A puts it everything in some bag and locks that bag. Okay, whose key is only with A. That's the idea, right? So in some sense, A, like locking is like some E of X. Okay, and such that D of Y,
Understood.
D of Y or D of X is known only to A. So maybe I'll call it EADA. Is that fine? So A puts her lock to the message and such that it's only known that unlocking is only known to A, to no other person. Fine. But for the timing, you assume like A can lock the bag and send it to B, and it's safe then. Then what B does is again lock it and send it to A back. Right. So now there are two locks for that bag, and A takes her lock back. So A unlocks her lock, and still there is one lock locked by B, and A sends it to B. So still there is one lock. And then B gets the bag with lock of B, and B unlocks it with his A, and B gets the whatever message inside that bag. So this is in principle the idea to send message from A to B or to exchange key without actually meeting. So this may be done through some courier or something, or by post. So A sends in some bag to B, and it's done this way. Like A sends it to B, putting A's lock, right, whose key only is only available with A. Are you Sanaita?
Yes, sir. So I just had a doubt. Why can't it happen in this way that the languages they were previously communicating in, they can just send a code through that language. Anyway, no one has hacked that language till now. So they can just send the code through that language and then it can happen. Can it be the case?
So at least once they should meet, at least once, right? So like for example, in situation like Corona, or maybe if they are staying at a very long distance, like one is in one country, other is in some other country, then possibly uh, it may not be possible like to meet even
No, sir, no,
once.
sir. I mean the way in which they were communicating before changing the language, they can continue that language and explain the other code or other language in their previously decided language to each other.
Yeah, I got it. But at least for their very first communication, before they started using some code language. So for their very first communication, they should meet, right?
Yeah, got it, got it.
So what you are telling is like once they started communication, for second, third communication, what you say that can be done.
Okay, so for the first time they're designing a code language, they have to meet, but when it's not possible,
Yeah.
this is the way they will meet.
Yes, yes. So I mean, some mathematicians put it this way, like, what if they can't meet, or can we exchange it through some by some method or through some channel which is safe? Okay, that was the idea. So I'm telling you the idea in principle. Uh, at the end, we'll see like how RSA gives this method to exchange the keys from A to B on a secure channel. So suppose A has some lock which can be opened only by A. So key is only with A, or in some sense that encryption function is such that even if other person knows it, that it can be opened only by A, and so on. So A will put her lock, send it to B. B will put his lock, send it to A. A will take back her lock and send it to B, and B will take his lock and B will open the bag. But then one risk in this is uh, B doesn't know that A has put that lock. So it's a belief that, okay, A has sent this back. And suppose A or that enemy, suppose pretends like I am A and sends wrongly to B some message to B, and B wrongly thinks that the bag has come from A. So there should be some kind of uh, or we should know in some sense like it has come from A, not from somebody else. So there should be some kind of what you can say identification that the lock is actually by A and not by some other person. Okay? And Diffie and Hellman put this idea. So like suppose A declares my lock is going to be like this and so on. So then nobody else can pretend to be A, right? That is the idea. So around 1976, around 1976, Diffie was from MIT and Hellman was from Stanford. they wrote a paper, and that was in principle. They didn't give any method practically. So can key be made public? So can you disclose that this is my law? So if everyone can uh, make it public that this is my law. Okay? So can key EX be made public?
Should not be made, then anyone can read.
So for example, if I'm using Caesar cipher, and if I make it public, I'm using E of X equal to X plus 3, then anybody, like say you or anyone can hack my message, and whatever message they get from me, then simply make it Y minus 3 modulo 26 mod 26, right? So that function EX should be such that even if people know E of X, so it should be possibly easy to calculate, but D of Y should be very difficult. Even if you know E, you won't be able, others won't be able to find D of Y. So that function E should be such that EX is easy, but DY is difficult. Okay, and that was the idea. Like, so this was just a paper. They didn't give any particular method, or it was in principle. Like, can we do this? It's a small paper actually. Yeah.
Sir, I have a
So
doubt.
yes.
Can you go to previous?
Yeah.
Here E of X is X plus 3. So D of Y should be Y minus 3 only, right? So there is no difficulty here.
Ah, yes. So we don't want such functions. We want functions where E will be easy, and even if I make E public, others won't be able to find E. That was the idea.
Yes, sir. So it is inverse of E, right? So they can anyway they can find it easily, right? So there is no way to make it. If we make E of X as easy, so D of Y should be easy, right?
Yeah. So for such functions, actually, E and D have same kind of difficulty level. But can we find out some functions or some systems, some methods where E will be easy, but D will be difficult? That was their paper. That was their paper.
So the answer
Can
to the question is no.
in fact, RSA came with one such example, and that's called as RSA algorithm or RSA system, and that's what we are going to see.
Okay,
Sir, if E is difficult, then what will happen? If E is also difficult?
No, if E is difficult for A to encode it will be difficult, because so E of X should be easy. What are that method used by A? So obviously for A wants to send message to B in some encoded language. So for A, it should be easy, practical. Easy in the sense it should be practically possible. But suppose if A declares, I'm using this method, I'm using E of X equal to this. Still for the others, like you or anybody third party, that D should be difficult. That's the idea.
Okay,
So,
sir.
so
Even if
idea.
E of X is made public, another person can encrypt using that method, but they cannot decrypt A's messages.
Yes. So this idea is called as public key, or any system based on this idea is called as public key crypto system. So this is the basic idea behind public key crypto system. Yeah. So in fact, so function E is easy, but inverse or function D is difficult to find, even if E is known. Such functions are called as one-way functions. And there is one more type in such one-way functions that is called as one-way trapdoor functions. So some information is kept secret or hidden, and that information is called as trapdoor information, as we'll see later from our example of RSA. And if you know that hidden trapdoor information, that secret information, then you will know like how to find D. So inverse function D can be computed after knowing that hidden information or trapdoor information. Yeah. So many people started trying on this idea. So Rivesh, Shamir, in fact, really many people started working on idea of Diffie and Hellman because they just in principle gave a paper, but they did not give any particular algorithm or method. And Rivesh, Shamir, Adalman from MIT, they came up with one such idea, and that idea is based on the fact that multiplication is easier than factorizing a number, and it will actually do that. Yeah.
So if we
So,
know that hidden information, we can decrypt it, right?
right.
Okay.
Yeah. But all these things will be more clear once we do complete that RSA. So right now I'm not saying more things about that. So what is hidden, what is secret, etc. Will be clear from that example. Yeah. So so that RSA is after these three names: Rivesh, Shamir, Adalman. It's a short form of these three: RSA. Okay. So anyway, so they gave a practical algorithm to practical algorithm where E of X is, even if you make it public, D of Y will be difficult. Nobody could find D. Yeah. So the idea was based on this fact that taking product is easy, but factorizing a number as a product of primes is difficult. Okay. And here are three examples. You can just try them to get the idea, like really factorization is difficult, but the product is easy. So first we'll try to factorize it. What I mean by factorization is, like, for example, say 12, I can write as 2 into 2 into 3. That's the prime factorization of 12, right? And of course, 12 is a very small number, so I could factorize easily. But if you have some very big number, and in practice, they take numbers of the form, say product of two primes, distinct primes, which are about 500 digits. So they are so big numbers. And then if I make my n public, and then the decryption essentially depends on the factors p and q, then I have to factorize that large number n, which is very difficult in the sense like it will take a use time. And if it takes time, say for example, if I want to factorize some number n, and if I take a month or 2 months, then uh, it's practically of no use, right? Suppose in a situation like war, I have to send some messages every day, and if I want to decrypt some enemy's message, I should do that as fast as possible. If I do it after 1 month or 2 months, that is practically of no use. Okay.
So you
So
said
what
n equals
so
p
what
into
are today's algorithms and what are today's speed of computers? They are not enough to factorize huge numbers, big numbers as product of primes.
So,
Yeah.
so
So
decrypted system.
will you say it again? I could not hear. Listen.
Sir, how will the other person decrypt it?
Yeah, that everything we'll see in that RSA algorithm. Yeah. So right now for you the question is like factorize these three numbers, and I'll give you some time. So see if in that time you can factorize it. But as far as possible, don't use any calculators or any programs or something. Yeah, Kavina, you raise.
Sir, yes, sir. So you said n equals p into q, right?
Ah.
Can you explain that part again?
So in fact, RSA in their algorithm use some number which is product of two distinct primes, which are very large, which are too large, like almost 400 to 500 digits, or nowadays little more than that.
So p is 500 digits, q is 500 digits.
And they make n public, n public. But still, if even if you make that n public, for decryption, what you need is factors p and q. And to factorize n, given n, to factorize n is difficult. But if I want to multiply p and q, that is comparatively easy job, even if they are so big. So multiplication is easy, but factorization is difficult. That's the idea. So taking products is easy. Factorization is
So,
difficult.
sir, so the message is in p and q.
No. So the factor that decoding or decrypting function D depends on P and Q.
Okay, sir, you wrote 500 digits, right? So p is 500 digits and q is 500 digits.
Yes.
Okay, sir.
Yeah, Anahita has got one answer. Yes, Anahita, that is correct.
Yeah, sir. And I just wanted to ask a small doubt as well. You said that RSA number are huge numbers. Like as right now, Kavina said that 500 digits into 500 digits. That's known as an RSA number, right?
Yeah.
Okay. Thank you.
So try to do it manually, and you'll understand the difficulty level. So for example, let me write this first answer because one of you has got it. So it's 23 into 89. And you see, these are just two-digit numbers, but still to factorize it takes a little bit time. And if you have numbers which are 500 digits big, and you factorize some number which is product of two such primes, that would be too difficult. So, like for example, suppose if I factorize 36 as, first of all, 6 into 6, whether that 6 is prime or not, that again I have to decide. And if it is not prime, I have to further factorize it. So that is my prime factorization. Okay. So even if I factorize it as product of two numbers, again further job is whether they are really prime or not, or else I have to factorize further. Okay, so you can just copy these numbers and keep trying. I'll go to next page because we will complete RSS system. Just copy down those numbers.
Copy it, sir.
Yeah, and now actually multiply these numbers, and you see multiplication is easy. It will take lesser time than factorization. Or particularly for such problems, you can use some Vedic math techniques. So like, for example, if your number is near the base, like 10, 100,000 and so on. So this is 1000 minus 3. You have some nice Vedic math techniques. Multiply. This is 009, product of these two. And then this minus this, or this minus this. Anyways, 9.
multiplication can be done in various ways, but like
Yeah,
factorization,
yeah. And you see,
various.
multiplication is much routine, so that will take very less time. For example, this is 2047. So tell me answer for the third one. You can put in chat box. In fact, this number is 2 raised to 11 minus 1, and they are typical numbers.
So which is 2 raised to 11 minus 1?
That first one, 2047.
Okay, okay.
Sriya, so in some sense, you have only trial error in, or there may be some good computer algorithms for that, but you can do it this step by step, like whether 2 divides the number, if not 3 divides the number, if not 5 divides the number, if not, and so on and so on. Okay, so that's the only way. Or there are some techniques like Fermat's factorization method, or there are some other algorithms also. Yes, so this is 2 raised to 11 minus 1, and in fact this number is 2 raised to 23 minus 1. So it says something about these numbers. So number of the form 2 raised to n minus 1. If it is prime, if this is prime, then that implies n must be prime. Okay, or in other words, I'll say the same statement in different language. If at all n is composite number, then that implies 2 raised to n minus 1 is also composite. Okay, but if n is prime, always it may not imply that 2 raised to n minus 1 is prime. It may not imply this is always prime. And these are such examples, like 11 is one such first number. 11 is prime, but 2 raised to 11 minus 1 is not prime. It gets factored as product of two primes. 2 raised to 23 minus 1 is one such number. 23 is prime, but 2 raised to 23 minus 1 is not prime. And such numbers are known as Mersenne numbers. And whenever it is prime, that is called as Mersenne prime.
We had done this in numbers in the class, or basic.
Yes, sir. In primary
Yes.
yes.
So there is a common program on internet called as, collectively they try to find such Mersenne numbers or Mersenne primes. That is called as Great Internet Mersenne Prime Search. So in group, collectively, they try to find larger and larger Mersenne primes. So as of now, largest one which they have found is 2 raised to 825 9933 minus 1. That's the largest so far known Mersenne prime. It was found on 7 December 2018. Yeah, so that's about such numbers. So shall we go ahead? So anyway, the basic point is taking product is easy, much easier as compared to taking doing factorization. Kavina?
So Mersenne prime is used to encrypt the message.
Yeah, they are used in those systems. like
Okay.
systems like RAC or something. Okay. So now towards the RAC algorithm, and we need some basics for that. So it uses Euler's theorem, Fermat's theorem, and so on. So I'll define what is Euler's phi function. Suppose n is a natural number. Shall I say n belongs to n? It's a natural number. What are natural numbers? Like 1, 2, 3, 4, and so on. And I define phi of n is the number of integers say k, where k is between 1 to n, and GCD of k and n is 1. This is symbol for GCD. Greatest common factor of k and n is 1. So they are called as co-prime numbers. So you count how many numbers between 1 to n are co-prime with n, and that number is called as phi of n. So for example, let me calculate, say phi of 8. Okay, now you look at 1, 2, 3, 4, 5, 6, 7, 8, and look at GCD of every number with 8. So 1 with 8, obviously GCD is 1, common factor is 1. 2 and 8, GCD is 2, so it's not 1. 3 and 8, GCD is 1, so this is co-prime. 4 and 8, GCD is 4, so it's not co-prime. 5 and 8, GCD is 1. 6 and 8, GCD is 2, so that is not co-prime. 7 and 8, GCD is 1. 8 and 8, obviously GCD is 8. So what is phi of 8? How many numbers are co-prime? There are 4 numbers which are co-prime. Okay.
Sir, n belongs to, so that that is in or n, sir?
That is symbol for natural numbers. So in mathematics, they write not the usual n, they put one extra line. Reals are written like this. Rationals are written like this. Complex numbers are written like this.
Okay.
Yeah.
Sir,
Yes.
all of those numbers have to be co-prime, or is it like pairs you have to find?
1 and 8 are co-prime. So you have to count how many numbers between 1 to 8 are co-prime with 8. So you count like 1, 2, 3, 4. There are 4 numbers which are co-prime.
Okay, sir. Okay. Okay. Yeah.
So you can compute some numbers on your own later on as practice. Yeah, so here are some numbers. Phi of 1 is 1, and that is just because 1 is co-prime with 1. Phi of 2 is 1, because out of 1 and 2, 1 is co-prime. Phi of 3 is 2, because 1 and 2 are co-prime. Just a minute. Yeah. Phi of 4 is 2, so you can, by definition, you can compute phi of n for smaller numbers. But for larger numbers, there is a nice formula. So these are phi values for first 15 numbers. And you see some patterns there. Like for a prime number, you can see it's always just one less. So check phi of 5 is 4, phi of 7 is 6, phi of 11 is 10, phi of 13 is 12, because every smaller number will be co-prime with prime number, right? Yes, Anaita?
Yes, sir. I just had a doubt that why we are considering number of integers k and not natural numbers k.
No, they are natural numbers. Because actually, as I said, integers, but they are between 1 to 12. So they are natural numbers.
Okay.
Sir, how will we use this in cryptography, this phi?
We'll see that. Yeah, we'll see that. So in fact, I need this for Euler's theorem. So I'm defining it. Yeah.
should we copy this phi of 1 till phi of 50?
No, later on, it's so as such, it's not needed for lecture, but later on, I'll give this as a PDF for your reference.
Okay.
Yeah. So let me go ahead. So for example, if P is prime, I'll just do the necessary observations and write down here. So if P is prime, then phi of P is P minus 1. Then moreover, if at all some two numbers are co-prime, there is no common factor, then phi of product m into n is phi m into phi n. So that is called as multiplicative nature of the function. So such functions are called as multiplicative. And for all these things, you can refer to any standard number theory book. So like for example, at the end, I have given some references. So number theory by Burton, it's a nice reference to start with. Okay, and then using this property, you can have a nice formula for phi of n. So suppose if n I can factorize as product of primes. So like p1 raised to some power, p2 raised to some power, so on up to pk raised to some power. So for example, suppose say 72 I can write as say 2 cube into 3 square. Okay, that's the form. Then phi of n has a formula n into 1 minus 1 by p1, 1 minus 1 by p2, so on up to 1 minus 1 by pk. So that is fine. Okay, so for example, let's find.
Sir, I didn't understand this n equals statement.
So there is formula for phi of n in terms of its prime factorization. So if n has a prime factorization in this form, say for example, 72 I can factorize as 2 into 2 into 2 into 3 into 3. So I'll write it as 2 cube 3 square. So some prime p1 raised to some power, p2 raised to some power, so on up to pk raised to some power. So suppose it is product of k prime factors, then we have formula like phi of n is n into 1 minus 1 by p1, 1 minus 1 by p2, so on up to 1 minus 1 by pk. Okay. Anyway, so we won't need it here. So what we need is just this one. Suppose if n is a product of two distinct primes, so pq, where pq are distinct primes, they are prime numbers, then what will be phi of n? So by this formula, phi,
P minus 1 into q
minus
minus
1 into q minus 1.
yes, so it's phi p into phi q, right? And that is p minus 1 into q minus 1. But still, it's a multiplication, and as far as computer is concerned, addition always takes lesser time than multiplication. So we'll try to bring it to additive form. So I'll make it more simple. So p into q minus p minus q plus 1. And you see this is original number n. I'll take this one here. So it's n plus 1 minus p plus q. And again, you see for a very big number n, which is almost like 800, 900 digits, how should I find phi n? If I have no formula, else, or if I don't know those factors p and q, I'll check each and every number, like 1 with n, if GCD is 1, 2 with n, 3 with n, and so on. And that's a very long, tedious process, which will take time of about 1 or 2 months. Yes, so phi of n has a nice formula. In this case, it is n plus 1 minus p plus q. So provided I know those p and q, I'll know phi. Okay, so it's simple addition subtraction. N plus 1 minus p plus q.
Sir,
Yes.
sir, I did not get the last step, like n plus 1 minus p plus q. Like, what did we exactly do?
I have simplified just this. So PQ is n, and I have combined this one here.
Oh, sorry,
So it's
got it.
n plus 1 minus these two terms together.
Yeah, sorry, got it.
Okay, yes. So these are the basics which we need for Fermat's theorem and as well as for RSA algorithm. So those who are interested in number theory and some challenging problems or Olympiad problems, here is one problem for you. So suppose if I know n is product of two primes PQ, and if phi n is also given, then from n and phi n I can find out those PQ. Otherwise, you see, for such a big number, to find the factors P and Q will be difficult. So this is a challenge for you. Right now, I'm not solving it, or we are not doing it.
So just a minute.
Sir, will you tell it in the next period if we are not able to solve?
Yeah, but you will get it. I mean, it's not. So this is
Your last
actually,
session.
this is from RMO 1992. So even if you search on internet, you'll get a solution. But try it yourself first, and if you don't get it, then only look for solutions.
Then we can only find the value of P plus Q only, right? We can't find the value of P and Q, right?
But n is PQ. So once you know PQ and once you know P plus Q, you can find P minus Q. And
basically a quadratic individual.
yes, yes. So then you can find P as well as Q.
So how to find P minus Q?
So P
What is
minus
your with the two equation?
I could not get how to solve this problem.
no, anyway, it's not right now relevant here.
Know how to solve it.
So P minus Q square is P plus Q square minus.
Sir, I have almost solved, sir.
Yes, sir. Even I have almost solved.
Yeah,
One
so
thing.
those who have got it, you can put answer in chat box to me.
Can you please explain how to solve this?
No, right now this is not our actual interest for this RS algorithm. Just as a challenge, I gave problem related to that. Yeah, so it's one such interesting problem based on that n and phi n. I think we'll go ahead, right? Because we have to complete RSA. And anyway, this has no connection with RSA. So just as a challenge, you can take it. Okay, Fermat's little theorem. So Fermat was a French mathematician, and he is more famous for his last theorem, Fermat's last theorem.
Sir, may I state the Fermat's last theorem, sir?
But what we want is little theorem right now. So
Yes, sir. Yes.
so what is Fermat's little theorem?
Sir, if A is a number which is not divisible by P and P is a prime number, then A raised to P minus 1 is congruent to 1 mod P.
Good, yeah.
Yeah.
So Fermat stated that if P is a prime number, then P divides A raised to P minus A. So this is notation for P divides A raised to P minus A for any integer A.
So there are also these special primes, right? Like which are not really prime, but they work in this case. Like for example,
They
561.
are called pseudo primes.
Yeah,
So-
pseudo.
Yeah.
In fact, they are called as the ones which you are taking. They are Carmichael numbers. So pseudo prime is to some base, like which works for A equal to 2, A equal to 3, or so
Yes,
that is
sir.
pseudo prime to base B. Right?
Yes, sir.
If it's true for all bases, that is called as Carmichael number.
They used to think that you can get primes from this method, but then
Yes,
later
yes,
it proved
exactly.
that you can't do
Yeah.
that.
So in some sense, like is the converse true for Fermat's theorem. Okay. Yeah. So Fermat stated that P divides A raised to P minus A for every integer A, and if I take A common, I'll get a raised to p minus 1 minus 1. So because p is prime, p will either divide this number or it will divide this number. So if at all p does not divide a, in that case GCD of a and p is 1, and in that case p will divide a raised to p minus 1 minus 1. And such results are useful for calculations, because once I get something is congruent to 1 mod some number, I can take higher and higher powers, and this side I get only 1. So that's useful for calculation. So this is Fermat's little theorem, and Euler made it more general.
Sir, can you
Euler
please
version.
explain this again?
What?
Sir, can you please explain this again?
Yes. Yeah. So from where you did not understand, this is okay. Like if p
Yes,
is a
sir.
prime number,
Yes,
yeah,
sir.
if
This is
p is a
okay.
prime number, p divides for any integer a, it divides a raised to p minus a. Okay, so like for example, let's look at some example. Say 5 is prime, and if I take 4 raised to 5 minus 4, then 5 divides 4 raised to 5 minus 4. Okay. So this is true only for primes, and Euler made it general for any n.
Sir, A should be in a composite. Is there anything like that?
Any number.
Sir, and what is the last line? A raised to the power p minus 1 is congruent to 1 mod p.
So which means p divides their difference. So p divides this minus this. We have used congruence in even in our Caesar cipher, like there it was modulo 26, right? So a raised to p minus 1 is 1 mod p, means p divides a raised to p minus 1 minus 1, the difference. Okay. Or when I divide a raised to p minus 1 by p, the remainder is 1. That's another meaning.
Okay.
But this result is true only for primes. Like if you try for composite numbers, it's not always true.
Sir, composite number most of the times it's not true, because pseudo primes are more rarer than normal primes.
Excuse me, sir.
Hello, am I audible?
Yes, sir.
Yeah, actually, there was some internet issue.
Sir, is there any way to prove this?
Yes, there
Yeah,
are.
it actually has a very elegant proof, but I kind of forgot it.
Okay, all of you, can you see the screen?
Yes,
Yeah.
sir.
Okay, yeah, fine. Yeah, it has a proof. In fact, there are so many proofs, and right now that's not our interest.
Sir, the
So,
most elegant one is they write all the numbers and they show the module, and then they add all of them and show,
Yeah.
right?
And then they show that it must be
Yes.
congruent to 1.
actually, the simplest one
That's
is
an elegant.
induction.
Yes, sir. Induction we can do it.
Yeah, by induction.
There
we
is
can-
a much more elegant proof that.
Excuse me, sir.
Yeah.
Sir, can you repeat how did we get GCD as 1?
Like p is a prime, right? So integer a and p will always have GCD as 1, I guess.
Which step you are saying?
The second step.
So I'm taking a common, and therefore p divides a times a raised to p minus 1 minus 1. And for a prime number, if p divides the product, then p will divide one of those numbers. So p will either divide x or p will divide y. One of them, which is not true. Which is not true in general for composite numbers. So it's true for prime numbers. So if GCD of a and p is 1, so if GCD of a and p is 1, that means p doesn't divide a. In that case, p will divide a raised to p minus 1 minus 1.
Okay.
So in other words, in congruence, I can write this statement as a raised to p minus 1 is 1 mod p.
So now, how did he derive it from that? Is there any steps in between?
No, that proof, etc. is a different part. So right now, that is not our interest. So our interest is RAC. Okay. So more generally, I mean, this is true for prime, but more generally for any n, it's not true. Like for example, suppose instead of p, if I take 4, which is not prime. So then you try like 3 raised to 4 minus 1 is not congruent to 1 mod 2. You can try it for composite numbers. And what Euler proved was, that is Euler's generalization of Fermat's theorem. So what Euler proved was, if GCD of A and N is 1, then A raised to phi n is 1 mod n. That is
And
Euler's
since
generalization.
phi of p is always equal to p minus 1, then it's a special case of Euler.
Yeah,
Okay.
yeah. So if n is prime, then phi of n will be n minus 1.
Sir, I have sent you the answer of the theorem question, sir. Is it right, sir?
Yes. Yes. Yeah. So shall we go ahead?
Sir, so phi of prime is basically prime minus 1. That's why it is working.
Yes. Yes.
So,
So,
sir,
so that was generalization by Euler of Fermat's theorem.
sir, can you go to the previous slide for 1 second?
Yes. Yes.
Thank you, sir.
Yeah. Okay. And now we are almost towards the RSA algorithm. So this is picture of those 3 persons, Rivesh, Shamir, Adalman. And I don't know who is Rivesh, who is Shamir. So Rivesh, Shamir, and Adalman. So they were all 3 from MIT, and they were friends. And Rivesh and Shamir were the computer scientists. And Adalman was mathematician. So the story is like after that Diffie and Hellman's paper, Rivesh and Shamir got interested in the problem and they tried to find some such function which can be made public. And Adalman was not interested in problem actually. So because they were just friends, Adalman agreed that he'll check what are the method they developed. So every time, so they gave some method and Adalman found some mistake or some gap or some loophole in that method or in that algorithm. And they almost did it for 41 times. And I think for the 41st time, it was foolproof. And Adalman said, okay, this is fine now. And this is foolproof. So then Rivesh and Shamir wrote a paper stating in the beginning names of those 3 people, like Adalman, Rivesh, and Shamir, and showed it to Adalman. Just go through it and check once whether everything is correct or not. And Adalman said everything is fine except my name because I don't want my name for this paper. It's all your work. So I just check whatever you have done. And finally, they agreed that, or I mean, Adalman agreed that you can put my name at the end of the paper and not in the beginning of the list of authors. And so the name is RSA rather than ERS. Otherwise, all scientific papers, they write in the names in alphabetic order. Like it should have been ARS otherwise, but because of this story, it's RSA. Right? Yeah. So Rivesh and Shamir essentially developed that algorithm, and Adalman's job was just to check whether it's foolproof or not. almost they attempted for 41 times. And ultimately, they could succeed in some method, some algorithm, which is based on this idea of public key crypto system. Yeah, so we have 15 minutes now. So the last part, the key generation. Now, if you have some doubts, you can ask me at the end because this is something difficult. So don't interrupt in between. So I'll answer all your questions, doubts at the end. Yeah. So how is the key generated? So it's towards like E of X. Okay. So choose two large primes P and Q, and they are usually about 500 to 400 to 500 digits. And nowadays I've heard they choose it even more bigger. And compute n equal to PQ, that n is called as RSA modulus. And once again, taking product is easy, so this can be done in some reasonable time. That's the idea. So side by side, I'll take some small example just for your understanding. So suppose P is 11 and Q is 3. Of course, we can't work here with huge numbers, big numbers. So n will be PQ, that is 33. Then compute phi n, and for large numbers, you can find out phi n by just this formula, which we saw some time back. So pi of 33 would be 33 plus 1 minus 11 plus 3, that is 14, that is 20. But in this case, because I know those factors are small, I can factorize it. It's pi of 11 into 33, and I can separate out. So pi of 11 is 10, pi of 3 is 2, it's 20 in any case. Select at random some number E, which is between 1 and phi n, such that GCD of E and phi n is 1. And again, choosing such random E for big number as much as phi n, that can be done in some practical time because of prime number theorem. So just believe that such E can be selected in some reasonable time. It's not something difficult. So for example, let's choose in our case, say E equal to 7, and see that GCD of 7 and 20 is 1. And whenever GCD is 1, you can find its inverse. So for 7, I can find out some number D, says that 7 into D is 1 mod 20. In this case, it's simple and you can just do orally.
It's 3.
Yes, 3.
So can you tell me what should be D in this case?
3, sir. 3.
Yeah,
3.
so D is 3 because 7 3s are 21 and 21 is 1 mod 20. If I divide 21 by 20, a remainder would be 1, right? So D turns out to be 3. And this E is the enciphering or encryption exponent, and D is decryption.
How will we use E and D means exactly?
That we'll see on next page.
Sir, how was D3?
This is just by some trial error because now numbers are smaller, but otherwise, like how that can be done is using Euclidean algorithm. So if
Okay,
GCD,
sir.
if
So where did
GCD,
we use?
if GCD of 7 and 20 is 1, I can find out some suitable integers x and y, such that 7x plus 20y is 1. So for example, 7 3s are plus 20 minus 1s are. But this can be done by Euclidean algorithm for big numbers. Because it's small, here I'm just directly giving the answer.
Yeah, using linear Diophantine equations, 2 variables.
Yeah. So when I work modulo 20, this part will become 0. Therefore, I get 7 3s are 1 modulo 20. Right?
So can you repeat this last equation, that 7x plus 20, why we are doing
Yeah,
that?
so when I work modulo 20, that part is 0. When I take multiple of 20, it will leave remainder 0 when I divide by 20. So it's like modulo 20, this part is 0. So I can say 7 into 3 is 1 mod 20. So my D is 3, inverse is 3.
Because I couldn't get that. Can you repeat?
Okay, and now out
So
of
that
all
symbol in the third step, is that 5?
5 for what?
Sorry.
What is 5? 5?
5 in the third step, that compute, is that phi of n?
Oh, acha, pi n is Euler's pi function.
Okay.
So also Euler,
Can you explain what that indicates, sir?
this was Euler's pi function.
The number of integers. Oh, okay, sir. Thank you, sir.
So can you go to the Fermat functions now?
Yes.
Where did we use Fermat little theorem in the tree generation?
I think it would be used in the
No, so
proof.
far we haven't used it. That is used for decryption purpose.
Okay. Sir, you wrote the last 7x plus 20y equals 1, right?
Just a minute, I'll come to that.
Sir, in this you wrote 7x plus 20y equal to 1. So you substituted x equals 3 and y equals -1. Why that's so?
So that, I mean, this is something very simple because for small numbers you can do it orally. This is known as Bezout's theorem, Bezout's result. But for large numbers you can find those x and y using some algorithm called as Euclidean algorithm.
So why we are finding 3 and -1?
So you get that inverse basically. So that x part is basically that d part, inverse part.
So basically, you can write it as 7 into d minus 1 is divisible by 20.
Yes.
So 7 into d minus 1 is 20y. So 7 into d minus 20y is equal to 1.
Exactly. Yeah.
So x is d here.
X is
D here.
Yeah, x is d.
d. Yeah.
Then
Sir,
why?
which theorem is this?
X is D.
Bezout's theorem. That is called as Bezout's theorem.
Sir, for Bezout's theorem to work, x and y should be co-prime, right?
No. In this case, GCD is 1, but in general, Bezout's theorem is true for any GCD.
So
because-
Bezout's theorem is same as Bezout's lemma?
GCD can be expressed as linear combination of those two numbers.
Oh, yes. It can be generalized. Okay, sir.
That is Bezout's theorem. Yeah.
Excuse
Yes,
me,
sir,
sir.
yes.
X is
Bezout's
d.
theorem same as Bezout's lemma?
Yes. It's not Bezout actually. The pronunciation is Bezout. It's a French name.
Okay.
Yeah. Yes, Kavin.
Sir, here x is d here. By using d, we are finding y.
In fact, when you use that Euclidean algorithm, you get x and y together. But here, because those numbers are smaller, you can just do it orally.
Sir, no, sir. In that RS algorithm, we didn't get -1, right? Where did we get?
Still, we have not completed RS algorithm. Still, we are.
So here -1 is the decrypting. So then, and one more thing, sir. And then how come 7 into 3 plus 20 into -1 equal to 1 becomes 7 into 3 equals 1 mod 20?
7 3s are 21, and 21 leaves remainder 1 when I divide by 20. So we call it as 21 is 1 mod 20, right?
So how that step leads to this?
That is by definition of congruence. So like A is congruent to B mod N if N divides A minus B. So like 20 divides 21 minus 1. So I say 21 is 1 more 20.
Oh, you didn't get the mod from those two, from that equation. You did it in the right hand side. You did it in the d equals 3.
I did not get your question.
So, sir, I'm asking that 7 into 3, the mod equation, does it come from that 7x plus 20y equal to 1?
Yeah, yeah. Exactly.
So how come, my question is how it comes from there?
So now you look at this equation, modulo 20, and modulo 20, this part will be 0. So 7x is 1, modulo 20. Okay. So that value of
So is
x
this
is
PPT uploaded in the Google Classroom?
okay. Yeah.
So 20y is modulo 20 here.
20 is 0, 20 is 0 mod 20.
So
See,
here,
if you divide 20 by 20, what is remainder? That is the answer.
this is 0.
Yeah. Okay. So yeah. So we have work E and D, and out of all these, N and E are made public. And as we said in the beginning, some information is hidden or secret. That's called as trapdoor information. So phi N and D are kept hidden. That's trapdoor. There are some raised hands, but I'll take your doubts at the end now. Let me just complete the algorithm. Okay, so now encryption is done this way. So like, for example, if A wants to send message to B and A has plain text, what A will do is take P raised to E and work it modulo that number N and send this to B. So B receives the ciphertext, which is essentially P raised to E mod N. Okay, and now the main job for B is to get back original message, that is P. And that can be done using following.
Sir?
Just a minute, let me complete this and I'll take the doubts. Okay. Yeah. So B has that C, which is P raised to E. Okay. And B wants to get back what is message P, the plain text. Okay. So what B does is take C raised to D. And what is C basically? P raised to E. So P raised to E raised to D. So that is P raised to ED. And what did we say? ED is 1 mod phi, right? So which means phi n divides ED minus 1. Or ED minus 1, I can write as phi n times some quotient k. So I can replace ED by 1 plus phi n times k. Is that okay? So this is P raised to 1 into P raised to phi n raised to k. So when I work modulo n, P raised to phi n will be 1 by Euler's theorem. So this is P raised to 1 into 1 raised to k mod n. That is by Euler's. And which is basically P. So this is just same as P modulo n. My P is smaller than n, so the actual value is P itself. And if at all GCD of P and N is not 1, still we can manage to show that C raised to D again gives me P. There we need Fermat's theorem. Yeah, so anyway, now let's try to analyze this. Like, suppose A is sending message to B as P raised to E, which is C, and suppose E also receives or E intercepts that message. How E should get back original message? So essentially, to get back original message, what B or E wants to do is C raised to D, right? So for Eve to break the code, she should know D. Once Eve knows D, what Eve will do is take C raised to D, okay, modulo n, and that will give the actual answer because n is public. So n is known to everyone, and therefore essentially Eve has to find that number D. But what is D? D is inverse of E modulo n, modulo 5. So ED is 1 mod 5, right? So E is made public, and therefore D, for finding D, Eve should know 5 because I have to take inverse with respect to what number. That should be clear to me. Then only I'll find D, right?
Sir, I have a doubt, sir.
Yes, just a minute. Huh? Let me complete this. So, so Eve should know 5, right? So that she can take inverse of E modulo 5. And to know 5 without factorization. So if you know P and Q, you have a nice formula for 5, that is n plus 1 minus P plus Q. But if you don't know P and Q, you have to practically find by checking each and every number right from 1 up to n. And n is so huge number, so large number. So to find out that with today's speeds, today's algorithm, it takes a lot of time, almost say 2 months to 3 months. And therefore, it's not practically speaking reasonable to find pi without any knowledge of P and Q. So basically, she should know P and Q, and that means she should factorize it. And factorization of n is difficult. So for that person to take product of P and Q is easy, but once I give you n, to factorize n as product of 2 primes PQ is difficult. So it's that is essentially the RSA algorithm, okay? Or there's the idea that like, factorization is difficult, but the taking product is easier. Yes.
Sir, but how can you take some power of plain text, sir? Like E means if I want to send AB, for example, means I'm sending you a message AB. Then how will I code it, sir? Means I will take A as 1 and B as 2, and then use this coding method and then send two numbers.
Suppose I have some number, okay? Say for example 12, okay? And I want 12 raised to 7 because our E is 7, okay? And we
sir, why would I want to send a number, sir? If I want to send a message, then
no, we are converting A to Z into some numbers, and
okay,
we'll send in terms of numbers, right?
Okay, sir, understood. I had this doubt. If I want to send text, how will I do it? Okay,
yes,
sir.
12 raised to 7. Now this you have to work modulo that number. So for example, in our case, modulo 33. And what you can do is like find out 12 square, okay, and yet you can reduce it modulo 23. So this is 144, and you divide it by 33 and find out remainder. So I think 144 will turn out to be some small number.
132.
But what if Eve uses means computer to factorize the n?
Still it's not possible. Yeah, so still it's not possible in some feasible time. Like see here, in case of wars or in some situations like where you want to hack certain message, there is some urgency. Like suppose, say for example, in today's situation, if Russia is sending some message and Ukraine wants to hack it, it should be immediately for that day itself, right? If you hack it after 1 month, that's of no use.
Sir, 12 square is congruent to 12 mod 33.
Sir, from where did we get 33?
We are just taking a number.
So this was our example. Just as an example, I had taken 11 and 3. So that was our error.
Sir, can
And
I go?
in practice, those n will be very big numbers.
Sir, here where we took -1, where we used -1 here.
Which -1?
No, sir, we found that y is -1, right? On that.
So that vanishes because 20 is 0.
So what, sir?
That becomes 0 because it's 20 into -1 and 20 becomes 0.
So because
We are
20
working
mod
model
20
of
is
20.
0.
So let that y be anything. It will become 0.
Okay, sir. Then at last you said the Eve should know P and Q. So
Yeah.
how come B knows about P and Q?
How come?
How come B knows P and Q, sir?
Yes, Meta.
Sir, 12 raised to 7 is congruent to 12 mod 33, sir. 12 raised to, the thing here is coincidentally 12 raised to anything is 12 mod 33.
Just a minute. Let me answer it. See that N and E is made public by everyone. So by A. So if A is using some N and E, A has made this public, right? And
Sir, can you please explain this decryption method once again?
just a minute. Just a minute. Let me.
Yes, sir.
Oh, so it's written other way around. So basically, what A will send is P raised to D, right? Because A knows D and E is made public, right? So what A B will do is P raised to D raised to E, and that is essentially again same.
C raised to E, sir.
Yeah. So that's a good one. Yeah.
So then how come B, so A is sending a message, so B should know P and Q so that they can.
We would know N and E because they are made public, and whereas what is kept secret is that phi of
Then
N and E.
no phi of N, we should know P and Q, right? So P and Q should be known by B also. So how come B knows about P and Q?
No, that's what I'm saying. It should be basically like C raised to E, so that we will know E and we will take raised to E.
Yeah, then how will we get P and Q here?
There is some confusion here. Okay, what's the time, Sriram? When
I think we
when is
have overshot the time by 8 minutes.
Oh, acha, okay. Oh, it should be P raised to E only. Yeah.
So can I go to the next one? This is the last slide, sir.
Yeah, in fact, yeah, just a minute. So I was confused a bit because of just a minute. So what he will do is he will use B's E because B. So maybe I should have written that NBEB. So this is EB. So E of B, right? And B knows his N, E, and D, and therefore this will be, yeah, this is correct. Originally is correct. So what A will do is take any plain text and make C raised to E, where E is E of B, which is made public, right? And what B will do is raised to DB. But to know that DB, basically Eve has to find out factors P and Q, right?
So what the last slide says, then the hidden message. Yes. The next slide.
See, everyone is making that N and E public. So like for example, A will make her choice public, like N and E public. B will make N and E public. So A will know everybody's E, right? So A will use B's E. So I'll call it EB and make C raised to EB, right? Modulo N, right? And that N is also B's N, right? And B knows his N, his E, and for B, everything is known. So B will know D also, DB also, right? So for B, all these three things are known, and others will know NB, EB. So what A will do is take P raised to EB mod N, EB mod NB, right?
So how come B gets to know all these things, but E can't do it? Can you repeat that again?
No, B, how B knows no, it's because like B has selected his own N and E. So B knows even D for his E, right? And A is using B's N and E.
Sir, if he uses B's N, A should
B
find
making,
phi of
B is
N.
making E and N public, and A is using B's E and N.
Yes, so when A uses B's N, he should know about phi of N. Then to know about phi of N,
For A is not decrypting, A is encrypting using that N.
so what A?
Using that E. See, what A is doing is P raised to E modulo N, and this E and N will be those which are announced by B. So they are used by B. So these are made public. So this is EB and NB. They are made public by B. So these are known to everyone by B. And for this, DB is known only to B. So nobody else can decrypt it.
No, sir, I'm asking when A sends message to B, like A encrypts by not saying the value of D. So how come B knows to the value of B A?
No, A will be using B's E and N. So, so for B, there is no problem to decrypt. B will do whatever that message P raised to D, P raised to E raised to D, right?
Okay, sir.
Yeah, so maybe we'll have to stop because.
So will you send this PowerPoint with these annotations?
Yeah, I'll send this as a PDF to, so that will be sent to your classroom, Google class.
Sir, and one more question.
Just a minute, just a minute. So let me show. Yeah, so these are some reference books. So if you find the subject is interesting, you should read or you should know something more about that. Then these are some books, and especially if you want the number theory aspect of cryptography, that Koblitz book is nice book. So I've done my cryptography through Koblitz book, but a good book with history and stories, etc., is by Simon Singh, Code Book, or even Khan's book, Code Breaker, also has a lot of history and stories related to cryptography. And some of you, maybe if you want to do some number theory or solve some more problems, then there is one reference, elementary number theory by Burton. Sriram, can I take the doubts for 5 minutes?
Or actually, we have one session at 6 o'clock.
Oh, okay. So should I stop then?
Yes, sir.
Yeah, okay.
Sir, what is
Sir,
the last two
you'll
states?
share. Sir, you'll
Yes.
share this PPT in the
Yeah, I'll
Google
share.
Classroom.
Yeah, I'll share this. Yeah.
Thank you, sir.
Sir, and what is the last two states? Can you go to previous slide one?
Yes, sure.
Yes, sir, this slide and before slide, you didn't explain this two things. Yes, sir, this and that.
So how this is about like how that original problem, like how that key should be exchanged from A to B on a safer channel without actually meeting. So that can be done using RSA algorithm. So it was originally developed for exchange of keys.
Sir, so the next slide.
So it's written on next page. So maybe right now we'll have to stop, and everything is clear there.
Sir, the same thing is said here, the key generation.
Yeah.
Okay, sir.
Okay, then bye everyone.
Bye, sir. Thank you, sir.
Bye.